So at the end of today's lesson, you should be able to answer the following questions. One, explain 5 reasons why a homogeneous equation is not always a correct equation. 2, you are told that the period T of an oscillating spring mass system depends on its mass, spring constant, on its mass and spring constant. Deduce a relationship between period T M and spring constant K. Expected answer is equals to T is equals to K M over K. Right. 3. Another question that you should be able to answer at the end of this lesson is the force F, it is the gravitational force. The gravitational force F between point masses M1, between point masses between 2 point masses depends on their masses M1, M2 and their distance of separation R. Alright, that distance of separation R. Deduce a relationship between F, M1, M2 and R. Right. The expected answer for question 2. The expected answer is F is equals to K M1 M2 over R squared. Question number 3 that you should be able to answer is the linear speed. The linear speed v in a wire depends on length L of the wire, tension T in the wire, and mass M of the wire. Deduce a relationship between speed V length L, tension T and mass M. The expected answer is V is equal to K TL over M. Right. So in today's lesson, we want to consider the 5 reasons why a homogeneous equation is not always a correct equation. Why homogeneous equation is always a correct equation? Reason 1. Suppose our original equation is x is equal to ut plus half at squared. This is our original equation. Then somebody says the actual equation is x is equal to ut. This equation is homogeneous. U is the linear speed, t is the time. Use the linear speed, t is the time, is the acceleration, t is the time, x is the displacement. So this is in meters per second times second, which is in meters. Therefore, this equation is homogeneous. But this is an incorrect equation. The equation is homogeneous but incorrect because of the missing term. So the missing term there, this is the missing term. So this term is missing. Somebody simply said our equation for displacement is ut. But this equation is homogeneous but incorrect due to the missing term. So the equation may have a missing term. Reason 2 why equation may be homogeneous but incorrect. How is that? Reason 2 equation may have an extra term. Our original equation is still this one. Then somebody said the actual equation is ut plus half t squared plus dt. Right? If you consider very well this equation, it is homogeneous. Right? It is homogeneous because this reduces to m meters per second times second plus half times meter per second squared times second squared plus meter per second times second. So this becomes m plus half m. S to the power minus 2 times s squared is 1. S to the power minus 1 times s is m. So the terms on the left hand side have the same basis as the terms on the right hand side. So this equation is homogeneous but incorrect due to the extra term. So this one is the extra term there. So it renders this equation incorrect. This extra term, right? This extra term renders the equation incorrect. Okay, third reason is that the equation may have wrong coefficients. Reason 3. Equation may have wrong coefficients. Still referring to x equals to ut plus half at. This is the actual equation, correct equation that was derived. Then somebody says that the actual equation is x is equal to 2 ut plus 1/3 at squared. This equation is homogeneous. This equation is homogeneous but incorrect. This is our left hand side. This is our right. All the terms on the left hand side have the same basis as the terms, but they are wrong coefficients. Wrong coefficients. The actual coefficient for ut is 1. The actual coefficient for at squared is half. But because of wrong coefficient, this equation is rendered incorrect. It is homogeneous but incorrect. Reason 4. Fourth reason. Reason 4. The equation may have wrong signs, right? Wrong signs. So signs are very important in an equation. So our actual equation is this one plus half at squared. Suppose somebody says the actual equation is ut minus half at squared. The actual sign is the positive, but this one there's a negative sign there. So this equation is homogeneous. If we were to check for homogeneity there, we would agree that this equation is homogeneous. So this reduces to m. This left hand side, right hand side. The bases on the left hand side are the same as those on the right hand side. So this equation is homogeneous but incorrect due to the wrong sign. Reason 5. Reason 5. Reason 5 or a final reason. Reason 5. The equation may have a wrong dimensionless constant. Right. Here I'm no longer going to refer to that one. I'm going to refer to this equation, 2 pi L over G. So this is the period of a oscillating pendulum. This is the actual correct equation. It is homogeneous. So if somebody said T is equals to 1 over 2 pi L over G, this equation is homogeneous, but it is incorrect due to the wrong dimensionless constant. This 2 pi is a dimensionless constant. So it should be 2 pi, not 1 over 2 pi. So it has a wrong dimensionless constant. So these are basically the 5 reasons why a homogeneous equation is not always the correct equation. Now we're going to apply homogeneity to derive physical equations. Application of homogeneity to derive a physical equation. You are told that the viscous drag force F acting against a sphere falling through a fluid medium. Depends on density rho of the fluid medium, radius r of the sphere, speed v at which the sphere is falling. Deduce a relationship between F, rho, R and V. It's very simple to solve this. It's very, very simple. So I'm saying F is directly proportional to rho to the power A also depends on R to the power B and V to the power C. Right. So we're saying F is equals to K rho to the power A, R to the power B, and V to the power C. So the base units for F are kg meters per second squared. For density is kg m to the power minus 3 to the power A. For R is m to the power B. Then there is m to the power C. So we should have kg meter per second squared is equals to k. K is depending on the proportionality. So we'll have kg to the power A times m to the power minus 3a times m to the power b times m to the power c times s to the power minus c. So we'll have kg m to the power s to the power kg meter per second squared is equals to k times kg to the power a minus 3 plus b plus c times m minus 3a plus b plus c times s to the power minus c. Right? So kg is to the power 1 there. This 1 is equals to a. M is to the power 1 there. So 1 is equals to minus 3a plus b plus C. Then minus 2 there is equals to minus C. So minus 2 is equals to minus C. So 2 is going to be equal to C. A is going to be equal to 1. Then 1 is going to be equal to minus 3 times 1A there plus B. Right? C is 1 already. So minus 3 plus 1 is minus 2. By the way, C is 2. So minus 3 plus 2 is minus 1. So 1 is going to be minus 1 plus B. Right? So finally, Finally, 2 is equals to B. So F is equals to K rho to the power A, R to the power B, V to the power C. So our final relationship linking F, rho, R, and V is rho to the power, our A is 1 to the power 1, R, B is equals to 2, R to the power 2, C is equals to 2, so V to the power 2. So our final answer is K rho R squared V squared. That is the equation linking F, rho, R, and V. Thank you for my teaching.